like it might cancel out.
I believe he's either going to go for the quadratic or he's going to try and factor it out.
Sorry about that. I'm researching internet problems at my house, and I think I have it figured out. But so good for you guys. You were discussing like, what's he going to do now? What was your conclusion? Like, why is this going anywhere?
Well, we talked about factoring it out. I just did it. It looks like it might cancel. So.
Yeah, well said. So I just had circled, it's very important that X be close to 1, right? And so here's the language, and I mentioned this a little bit yesterday, but this is the language of calculus. Like, how do I say that? Well, I just wrote it in English, but this is how mathematicians say that. And that's why I left some space over here. We're actually looking for this, for the limit of this fraction as X gets really close to 1. As X goes to 1. Do you understand that that's the same statement that I have circled up there? X is close to 1. It's just that mathematicians do not like to write words. I don't know why that is. Like, they hate English. What is it? I don't know. They like symbols. Now, of course, can you let X be equal to 1? What happens to that statement? What happens to that fraction at X equals 1? Like, why let X get close to 1? Why not just let X equal 1? Well, if you do, hence, you end up with 1 squared plus 2 times 1 minus 3 over 1 minus 1, and you get 0 over 0. In other words, boom. Is that an explosion? It breaks, and the slope is, well, it just doesn't work. But of course, if we're someplace on the curve, as we looked at a little bit yesterday, there is a slope here, and so it's like that doesn't work. And again, that's the magic of not saying just let X equal 1, because remember, the 2 points touch and it explodes. They're the same exact point. Of course it explodes. And so that's the magic of this statement here, saying that the limit gets extremely close to 1. Now, what I would like you to do on your calculator is play around for a second, and let's let, and I want to show you some language of, let's let X get close to 1. And notice where I put that little plus. It's kind of like up there in the exponent. What that means is the high side of 1. Let's let it get close to 1 from the high side. In other words, 1.1 or 1.01. If we said, let's get close to X from the low side, negative, that'd be like 0.9 and then 0.99. In other words, what does it mean to get close to 1? It doesn't mean you have to come from the top. My drawing up here shows that X was bigger. Does that make sense? I'm saying that, X is on the high side. My drawing shows X to be more than 1. It doesn't have to be more than 1. It could be less than 1. But I want you to type into your calculator, like, what happens? What is the slope? I'm going to write a couple of these down myself. But like, what's the slope when X is, let's see, how am I going to do this? X is, let's put X over here. And I'm going to say like 1.1, 1.01, 0.9, and then 0.99. Like, what do you get for those slopes? This is what we did yesterday. We said we can't let the 2 points touch, so let's just let it get close and see what we think. Like, let's see what the limit approaches. It doesn't work to pick one, and so I'm going to take this expression here and type it in my calculator with 1.1 in it. And notice you could screw this up because you need some parentheses in your calculator to do this. So 1.1 squared plus 2 times 1.1 minus 3, close the parenthesis, all of that divided by 1.1 minus 1. When I did that, I got 4.1 for the slope. Now remember, a second ago, we did an estimate and we got 4, and so that's good. Like I got something near 4, of course, that makes sense. So if I choose 1.01, that's even, the 2 points are even closer, so I should get something even closer to 4. Maybe I'll get 4.01 or something like that. I don't know, I'm just guessing. I'm going to put a 1.01 in there. Really close now. And yeah, sure enough, I got 4.01 for a slope. Now I'm going to go back and try 0.9 into that expression. Since I can't show you my calculator easily, please interrupt if you're, saying like, what are you doing? I'm going to try 0.9 first. When I stuck 0.9 in, oh, that's kind of predictable. I got 3.9. In other words, the slope was on the underside. Now let's just take a look at the graph for a second. If I'm right and the graph is really right here, and this is x is 1, forgot what the y was that went with that.
-3.
-3, thank you. Doesn't it make sense if I'm up here that my graph would be steeper? If my second point was down here, then my graph would be shallower. So that kind of makes sense. I was under 4, doesn't it? Do you agree now that there's a pretty strong case that the exact slope is now 4 because I'm kind of dancing around 4 on both sides of it? I don't even think I have to plug this in. I think if I put 0.99 and I think I'm gonna get 3.99 for the slope. And so I guess
the limit would be 4.
Yeah. My hypothesis is that the slope is equal to 4. In other words, the limit would say that the slope is actually 4. So again, we're trying to get the instantaneous slope. We really don't want 2 points. And so again, do we need calculus? Have I taught you any calculus yet for us to answer the slope at that point is 4? No. But keep in mind, if you don't have one of these, like nobody has had until the last 50 years or so, just to do what we just did is a miracle. Like I put 0.99 in there. Can you imagine how long that's going to take if you just have paper and a pencil and you know how to do multiplication with decimals and so forth? Like it's going to take us 30 minutes to get these 4 answers here I just got and even hypothesize. But keep in mind, true mathematicians, again, you're pretty convinced this is 4, but that's because you're so used to whole numbers. But is there any reason that this couldn't be something that's just really close to 4? I mean, is there any reason it couldn't be 4.0001? I mean, you'd probably all bet lots of money it's exactly 4, and this is a pretty simple equation, and so it really is 4. But remember that there's no magic about landing exactly on 4. Numbers don't care. They could be somewhere ridiculously close to 4 and that'd be okay. So true mathematicians, this is not convincing. As I've been saying, for people that are, engineers or just want to use this stuff to do things in the world, just estimating it and saying it's approximately 4 is probably good enough to keep the bridge from falling down. So you don't need calculus to do what calculus does in the age that you live in, where it's really easy for us to punch buttons. It's interesting. I was at this fundraiser dinner a couple years ago, and I sat next to this 80-year-old guy who was an engineer, and I was just asking him questions about it because he was kind of back in the slide rule days, which is where you got answers to math questions by sliding sticks past each other. And just listening to him talk, I could tell that the majority of what he did as an engineer was what takes you and I 2 seconds on a calculator, just because all of us can multiply a couple of ridiculous 3-digit decimal numbers together and get an answer, whereas not everybody could do that in his age because they're sliding sticks past each other. And so anyway, my point is you don't need calculus to come up with the answer to 4 here. So it's actually extremely important that, and I'll show you a little bit of this theoretically later, but it's extremely important that you at least understand logically that this 1 plus is sort of from the high side. That's what that little symbol means, the high side of 1. And then we approached it from the low side of 1, under 1. And both of them seem to indicate that we were on our way to 4. And the graph would indicate that, it was getting steeper when we were on the underside, and it was getting less steep on this one when we were kind of on the high side, and it was honing its way in or working its way to 4, which is extremely cool. Now, I'll tell you what we're going to talk about next time that's ultimately cool. And I heard some of you kind of hinting at this as you were going out the door, but in 2.3, this expression right here, x squared plus 2x minus 3 over x minus 1, x cannot be equal to 1, right? Because when we did that, it blew up. But I think I heard one of you say when I came back something about factoring. Does the top expression up there factor?
Yeah.
What does it factor to?
It factors into x plus 3 and x minus 1, and then they cancel. And this looks
Exactly.
just x plus 3.
Like, so that expression up there, this expression up here is kind of like the expression, I don't know, like 21/7. In other words, when you look at that, because you know math, you say, well, that's a really dumb way to say 3, right? Because 21/7 simplifies, right? So it's kind of complicated. Well, that's what you're looking at when you stare at this ugly mess right here. But it turns out that actually simplifies. What does it simplify to? Well, just like this simplifies to a whole number, well, so does this. Can x be equal to 1 now? You see how it can? Like there was sort of a prohibition against sticking x as 1 in before because it exploded. The 2 points were the same point, and yet that expression happens to factor, which is not a coincidence. It happens every time. And so now you can actually stick x as 1 in this. There's no reason not to. And what do you get when you do? Well, you get 4, the slope that we thought we were getting. And so we actually, that's a proof. Do you understand that? Like now we can say the slope actually is 4. And in the end, this is what makes calculus cool. So what I just showed you is sort of the first time that you don't have to do all this guessing and checking nonsense, wasting your time. And you can even say, I actually know the instantaneous perfect slope. And it does happen to be, because this is the simplest function I could make for you. Think about that. In order for slope to be interesting, it can't be a straight line. So if we leave the equations of straight lines to the harder equations, what's the simplest one I could make? Well, it's moving up 1 degree to an x squared equation. Now you have an interesting curve that has different slopes every place. But I can come up with sine waves and exponentials and all kinds of crazy curves. And this process won't be as easy in those worlds. But here it's extremely easy. So what you're going to be asked in this section, and what I just wrote in green is kind of a sneak preview. You're mostly going to be asked to do kind of what I showed you right here, which is just experiment around with an expression that somebody gives you. Experiment around with it and just see what you get. And you'll see it approaching something. We saw this approaching 4 from the high side. We saw it approaching 4 from the low side. 4 is a pretty recognizable number. And so we hypothesize that the answer must be 4. Like you're not even creating this. You're not even creating this yourself. I showed you where this stuff comes from. Again, this is kind of a 2.3 concept, because I feel like if I show you the 2.2 assignment, you don't understand, like, why am I even being asked to do this? But it's the process of the brilliant idea algebraically of not choosing the second point. Don't choose it. Don't pick a point that's really close. Leave it not picked. Just leave it as letters. And amazingly, you get this expression that factors. And because it factors, the prohibition of plugging 1 in goes away. And you're actually able to get the exact slope and never have to do any guessing and checking. That's what's kind of cool. And ultimately, what makes calculus cool is when as soon as I teach you something in chapter 3, I can stare at that equation right there and just tell you the slope by just looking at it. There's a shortcut. There's a trick. You don't even have to do what I just showed you. But we'll get there when we get there. So let me just ask you a couple random sort of more book related type of questions now. Like for instance, if I said, what's the limit of, I don't know, sine of let's see, I want to come up with something that's actually going to be good here. So I'm going to look at something I did before.
Good or hard?
Good question. Have you had a math teacher before? So that's a little weirder of an expression. Notice we didn't get this expression by, looking at a parabola. I just made up a fraction. Now, if I said, let's figure out what the limit of that is as x gets close to 2, would you agree that there's no reason I couldn't just put 2 in this time? Like, can't you just put 2 in? Now, you're never going to get a question like this in your assignment. But keep in mind, when the book says, like we did a second ago, what's the limit of this as x gets close to 1, that's kind of just like saying, well, plug 1 in. It's just that when you do that, you get 0 over 0 when you're actually doing this to find a slope. But of course, mathematicians take this concept of a limit and, I don't know if I want to say kind of ruin it, but make it more complicated than it should be. So you're not going to get asked this question, well, why not just say the sine of 2 over 2? There's no reason I can't do that. That's not going to produce 0 over 0. I'm going into radian mode. If I say sine of 2 divided by 2, it doesn't say error. It says 0.45. Great. Like, just put 2 in. You don't have
So
to
you
put
would just have to assume that's the limit. So
Yeah.
it's going to produce 0 over 0, even though you do get 0.45.
Well, no, it's not. In this case, it won't. Like in calculus, when we actually take some cool curve and we try to find the slope at a point, if you try to put 2 into a real fraction that comes from calculus, it'll be 0 over 0. But my
Okay.
point is in this case, you're more than welcome to put in 2.1 and 2.01 and then 1.99 and 1.999, but there's no reason you can't just put a 2 in. Now contrast that with this question. What's the limit of this as x gets close to 0? What's your calculator say if you put 0 into this? From the unit circled, you have to have your calculator. Little review here. Do you have to have your calculator to know what the sine of 0 is? Physically or mentally, you should in your mind say, okay, I'm at 0 degrees or 0 radians. And what does the sign tell you about the location of that point? Somebody tell us.
The y value?
The y value. And the y value of that point is 0. So this is 0 over 0. So in this case, you can't put 0 in. Does that make sense? Like, this is an example of something that would come up in calculus. And so what are you going to have to do instead? Well, in this section, and notice, unlike the previous problem, there's nothing you can do to this one. Like, you're not going to factor this or do anything cute. You're just going to have to put in some numbers close to that. So again, I'm going to try what I just did a second ago and say, okay, well, I wonder if I pick, now again, do things on both sides of 0. Like, I'm going to try 0.1 and then 0.01, and I'm just going to type that in my calculator, and I'm a little less comfortable with this, aren't you? So if I type sine of 0.1 divided by 0.1, that's not going to explode. I got 0.998, and then if I try it again with 0.01, you should be doing this with me. This isn't magic. This is really simple. Again, imagine people trying to do this without a calculator. Like, don't forget, you're standing on the backs of geniuses here. Like, the very fact that I can even find an answer to this, if I take your calculator away, your ability to investigate this suddenly gets a lot more complicated. When I did that, I got 0.9999. So now I'm going to go on the other side of 0 and try negative 0.1. Because remember, we got to consider both sides and say, well, what if we approach, I just approached 0 from the top. In other words, this, if you will, is what mathematicians call positive 0. And the positive's not in front. It's like kind of up in the exponent. So it's like high side of 0. And now I'm doing the low side of 0 stuff. So now I'm going to type sine of negative 0.1 divided by negative 0.1. When I did that, I got 0.998 again. When I try negative 0.01, I get 0.999 again. what does it look like the limit is? Like, even though it exploded over here, even though over here it broke, if I just guess and check a little, what does it appear that the limit actually is? What is the limit?
1.
Yeah. It appears it's 1, doesn't it? That's what you're doing in today's assignment. Just plug in stuff in that's close. This is not that complicated. Like, don't make this complicated. When it's complicated, we'll talk about it, but it's like, this isn't hard. Like, just plug numbers in. Again, what an amazing period of time we live in, where we can experiment, we can play with this stuff and come up with guesses like this so quickly. And people in previous generations couldn't do this. And, you know, you got to slide, this guy I sat next to is like sliding sticks next to each other to try to figure out what the sign of 0.1 is, and or looking it up in a table and stuff. So it appears that it's 1. Again, that's the concept of a limit. Try this in the same way. Let's see, let's go with dark green. You find the limit of this statement, x squared plus 2x minus 3 over x squared plus 5x minus 6 as x goes to 1. Now, again, if you try to put 1 into this, it won't work. I'll just save you a little time. If you put 1 into this, you end up with 0 over 0. So you have no choice but to try 1.1 and 0.9. Like, just punch it into your calculator, play around with it, and see if you can do the same thing. What does this appear to be approaching? I'll give you a second. So let's see, I'm doing this with you. I tried 1.1 and I got the limit as being 0.577. Anybody try 1.1, get the same thing?
Yeah.
Yeah.
Okay, that means I didn't get it wrong. Then I try 1.01 and I got 0.572. Notice I'm not so lucky this time. In other words, it's not approaching a whole number, so I feel like I'm landing out in the middle of nowhere. So now I'm going to go on the low side of 1. So again, in the language of calculus, we call this the high side of 1, 1 with a little plus up in the exponent. Now I'm going to go on the other side and try 0.9. And I got 0.565. So I'm over here on the low side of 1. And I'm going to go a little closer. I'm going to try 0.999 and like cut to the chase. There's no reason to waste time being, you know, pretty far away from 1. Why not try 1.000001 and just like cut to the chase? Or 0.9999999. Like, why start way the heck out there? I got 0.571. So what's your hypothesis?
0.5715.
Yeah, I mean, don't you find yourself looking like maybe Cody just did and saying, well, that was 1.01 was here and 0.999 was there. And so aren't we like maybe 0.5715, like halfway between or something like that? But don't you find yourself thinking, I don't think I'm going to be able to use an equal sign here. I'm going to have to use an approximately sign. Last time it was like, oh, 4, you know, I can just say 4, but notice we're landing in the middle of nowhere. Do you understand that? This is really important. Yet you can tell it's working. Like there actually is a limit to this. Do you understand that? In a sense, what you need to understand though, and this is, I don't know if you've ever thought about numbers this deeply, but you might say this is impossible to actually answer. You can say it approximately. And by the way, we don't have to stop there. As I said, couldn't we use 0.9999999 and 1.00001 and get even closer to the right answer? I'm just kind of quitting because I'm sort of tired and saying, well, it's about right there. But it might be that we can never actually get this answer exactly right. Well, unless this is like kind of from yesterday, maybe that's like e divided by 2 or pi squared divided by 7 or some, you know, weird number that I could never get. Or maybe it's not that hard. Maybe it's just something like, you know, 6/7 or, you know, 12/17 or some fraction. But I don't know about you. I don't recognize that. Do you recognize that decimal? If it had been 0.33333, I would have said, hey, isn't that a third? Like there's some I recognize, right? Just like you. Or 0.2. Oh yeah, that's 2/10 or 1/5. Like there, but I don't recognize this one. Now, again, I don't think this is good. You're not going to see a question like this in your assignment unless my open math was kind of smart enough to say, you know, answer it correct to 2 decimal places or something like that. And then you could, I think, say 0.57 here and then be confident you got it right. Does that make sense? Now, again, to steal a little bit of my thunder for tomorrow, unlike sine of x over x, is there something, so I'll even make myself a note here, 2.3, just because I want you to be thinking about this ahead of time. It turns out in calculus, there's always a way to get it exactly right. Can you do anything with this fraction up here? Can you do anything with that fraction up there? Well, yeah. You can actually simplify it a little bit. So let's just do that. Well, that top fraction, let's see, x squared. Didn't we have this a minute ago? This is x plus 3 and x minus 1. And the bottom one is x plus 6 and x minus 1. So, oh, look at that. They have something in common. And so those can cancel. Why is it cool that those just canceled?
Because you could plug in 1 now without it being 0 at the bottom.
Couldn't be said any better. Like, do you agree that the prohibition against sticking 1 in just went away? What do you get if you put 1 in for that?
Get 0.57142 and so on.
Yeah, you get 4/7. You know, I'm ashamed of all of you. You didn't even recognize that 0.572 was 4/7. Like you don't have it memorized. What's the matter with you guys? But if you type 4/7 into your calculator, you get the decimal that we were just approximating. And so, and I made this up to do this on purpose because the decimal that you get there is not something that any of us recognize. And how did I make this up? Just to let you in on my little secret here. I actually started with this. I started with this. And then knowing that the x minus 1s would cancel out, I said, well, then let's let x equal 1. And if I don't cancel these out, then 1 will screw it all up. And so when we're back up here, it's like we won't be able to put 1 in, it won't work. And yet when these cancel, I made the x plus 3 and x plus 6 such that when you put 1 in, you get something over 7. Does it make sense? If it had been 4/8, we would have been honing in on 0.5 and you would have all said, oh, I know what it is, it's a half, right? So sometimes you might recognize the decimal and sometimes you might not. But the cool thing about calculus is I'm just making these up randomly, playfully to talk about the concept of a limit with you. But when we get statements like this, as a result of saying, hey, I'd like to know the slope of this curve, we're always going to get fractions. And think about this question carefully. When we do this, trying to find the slope, why are we always going to get a fraction? Why are we never going to have something like, you know, what's
Rise
the
over run.
limit of x plus 2? Yeah, it's because it's rise over run. Like slope is a fraction, right? So we're always going to have this fraction. So we're never going to end up with something like, what's the limit of x plus 2? It's always going to be a fraction. And the other thing that's always going to happen is the one thing that you'd like to plug in, you won't be able to. Because plugging it in would mean the 2 points become the same and the thing explodes.
So if it was a whole number, it would just be that over 1.
Exactly. Yeah. Like a second ago, it came out 4 over 1 and you were all, you know, real happy because it was very recognizable. So this is why there's an entire chapter of the concept of a limit, simply because when you try to plug in what you want to plug in, you end up with 0 over 0. And so you think, oh, it's just broken. I guess I can't do it. I'll just throw it away and this doesn't work. But if you play around with numbers close to it, it does appear to be approaching something. And then it turns out there's an algebraic way because of, you know, doing some, in this case, factoring. There's some algebra that you can do to kind of make that possible. Let me give you another example. Let's see, what is the limit of, let's see, x minus 5. Am I smart enough to make this up on my own? I feel like I'm not. I want to stare at something. I don't want to make up something that doesn't make any sense. It's a good thing I looked. So what's the limit of that? And again, don't write this down because I'm going to erase it. But what the book is never going to say is what's the limit of that as x gets close to, say, 30. Why is that never going to happen in calculus? Is there any reason I couldn't just put 30 in there? No. Like, go ahead and put 30 in and get the answer. What is always going to happen in calculus? And I guess I'm asking you to take my word for this a little bit because you haven't seen this in play yet. But it's like, what's the one thing I can't stick in for x here that would make this blow up?
A negative number.
Negative number would make it blow up? Any negative number. What actual number, what single number would make it blow up?
The number that x is approaching.
What is that though? What would make this 0 0?
5.
Close to 5.
25.
25, exactly right. So again, this is an example of a problem you'll see tonight in 2.2. You're not supposed to know how to do any of this factoring or do the algebra. And in this case, the algebra is much harder. Like you can't just factor this. This isn't as nice as a squared equation. I keep showing you squared equations because those are the ones that you can actually do something with. Most of these in real math, you can't do much with. And so is there any reason you can't find this slope? Keep in mind, what's on the other side came from slope. I'm just, you know, not drawing all the pictures and so forth right now. We'll get to that in chapter 3. But okay, great. So you can't put 25 in, but can't you put in 24.99 and 25.01? So do that and see again what it appears that this is approaching. And maybe you'll get lucky this time and it'll be recognizable, or maybe you'll get unlucky like last time and it'll be 4/7. I'm going to give you time to like draw your own conclusion or, you know, gain your own hypothesis while I do something cool. Okay, you probably have an answer. Why am I doing what I'm doing right now? Why did I go over here? I'm asking you to read my mind, but maybe some of you can read my mind. Well, I'm about to want to know lots of answers. Like I want to plug in 5.0, or I'm sorry, 25.01, 25.001, 24.999. It's like that takes a lot of time to type in your calculator. Why not go to your graphing calculator and, you know, type this expression in. Type that expression in and just steal it from your calculator. But I'm going to do it in Desmos so you can see it. In other words, now that I'm here, can't I go over here and say things like, well, what's f of 25.1? Like, part of me wants to say, I think I can quit right now. I think the answer is 10. Is that what you got? So when I picked something on the high side of 25, I got 10.009. In other words, already I'm thinking, and again, I find myself, you know, I like whole numbers, don't you? So I find myself going, yeah, that's kind of cool. That seems to come out good. But of course I can go back here and stick in a 0, or why not just cut to the chase? Put a whole bunch of zeros in, all right? Like, it's not like you have to start at 26 and then go 25.5. Some of your book assignments will ask you to do that, and that's fine because they just want you to see it working its way to 10. But if the whole goal is to get something close to 25, why start at 26? Like, just get really close. And to sort of prove it, if you will, if I go on the, and I just want to do it twice so that you can see both of them. If I go to 24.999999, just throw a whole bunch of 9s in there. Notice, I don't know about you, but I was expecting to get 9.999 or something for that. Isn't that kind of weird that I got something that's like also 10? It's like they both came out on the high side of 10. That's kind of interesting. But the point is either one of them seem to be working their way to 10. And so I'm ready to bet money now. Like, even though I can't plug 25 in and I don't even know what algebra to do to kind of prove it's exactly 10, true mathematicians are not satisfied, remember, by just hypothesizing that it looks like it's 10 here. But I'm ready to bet money now. Does that make sense? And of course, from yesterday, what I could have done here that I'm only just going to quickly type is I could have said f of a and not even put a number in at all, except add that slider. And of course, if I put 25 in, notice f of a is undefined because it's 0 over 0. But of course I can, you know, I can just start typing stuff here. And I could just, you know, slide a around. I could just slide it around and watch what happens. But of course I need to stay really close to 25. I'll show you this because it's kind of cool. But since I don't want a to go everywhere, don't I want it to stay really close to 25? So I could say, let's go from 24.5 all the way up to 25.5. Like, I only want my slider to kind of stay close to 25. So I just gave it a, well, what is that called? It's a domain. Didn't I just make a domain restriction on it? That's what mathematicians would say. I restricted it, and then I'd like it to step a little smaller. Unfortunately, I'm not even sure Desmos will even do 0.01. It might only do 0.1. Let's find out right now. And notice there's that little play button over on the left. So apparently it does 0.01. So see, I'm just watching f of a, like, stay close to 10. I mean, that's just kind of cool. That's interesting. I just saw it go into the 9s. I didn't notice that before. That's weird. It makes me think I got it wrong. Over there, it does look like, you know, it's on the other side of 10. And so I don't know what happened with that 24.999. Maybe it was a rounding. Yeah, I guess it was. Isn't that interesting? That's kind of what I thought was going to happen right there. Stop. Stop. Disappear. That's what I thought was going to happen. So it must have been a rounding thing. So now I'm really ready to bet that the actual slope, you don't know about slope in 2.2's assignment, but I'm ready to say the limit of this as x gets close to 25, even though it can't be 25, it still approaches a limit of 10. So in calculus, it'll be like, yeah, the slope of that curve at x is 25 is 10. That's why we're going to be doing this. This is not hard. That's what I want you to see. So, you know, use your technology. Don't manually type this stuff in. Some of you probably didn't put enough parentheses in it and you didn't get something close to 10. So this appears to be 10. But as I said before, remember, there's no guarantee that it's 10. This is still just a decimal, and it just happens to be a terminating decimal. And there's not even any numbers past, oh, it's raining again, I love it. There's not even any numbers past 10. And so, but there's no reason this couldn't be 10 and 190, you know, like something like this, 10 and 192nd. There's no reason that couldn't actually be the answer. Does that make sense? I could still be wrong because we were talking about infinity. Remember, we're touching infinity. Have you ever heard of Zeno's paradox? Ancient people didn't have Netflix, so they came up with weird stuff like this. Have you ever heard of this? Probably the answer is no, but Zeno's paradox is this. If I am standing, if you're in your room right now and you look over at one of your walls and you say, I'm going to walk over to that wall, but you decide to walk there in a really unusual way, instead of just walking toward it until you smash into it, you walk toward it. Here's the wall. Here's you. You walk toward it by cutting the distance between you and the wall in half. That's how you're going to get to the wall. So I jump to here.
Oh, I've heard of this before.
Yeah, maybe you haven't heard the name, but you might have heard of this. And then you jump half again. So now that you're here, and then you jump half again. So now you're here. The paradox is, do you make it to the wall?
No, never.
Cody immediately says, no, never. Do you agree? Disagree?
If you're always having the distance, you'll never reach it.
And of course, you do have to think of yourself as a point, not, you know, you're a physical object. You might say, well, I don't get to the wall, but look at me inside. I got a big nose. My nose will hit the wall. So, I mean, there's a practical side of this, but Cody's right. If you stop walking, if you take 1 billion steps, you don't get there. But what if you take infinitely many steps?
That's true.
But the problem with that statement is you can't take infinitely many steps. Do you understand that? Infinity is not a number. It's not a big number. We can approximate it with a big number like 99 billion. If you take 99 billion steps, you don't get to the wall. If you take infinitely many steps, you do get to the wall. That's what we've been doing. Back here, what did we do? We got infinitely close to x is 1. And when we did, the answer was 4/7. We made it to the perfect answer of 4/7. If you get really close to 1 by picking 1.00000001, then you don't get to 4/7. Do you understand that? So the reason Zeno's paradox is a paradox is if you take a finite number of steps, you genuinely don't make it to the wall. But if you take an infinite number of steps, you actually do. But you can't take an infinite number of steps, and that's why it's like, you know, my brain explodes. In a sense, that's what we're doing with calculus. We're letting the second point, this is like the second point, and this is the point we're interested in, and we're saying, let's let those get really close. Well, how close? Infinitely close. If they get infinitely close, then you actually do get there, which is just weird. How about this one? Have you seen this one? .9 repeating. Is that equal to 1, or is it slightly less than 1?
Slightly less than 1.
It's slightly less than 1 if you stop adding 9s at some point. If you finally give up and say, I'm tired, you know, I have 56,000 9s and I got to go to bed now. Well, then you haven't made it to 1. But that little line over the top of it, how many 9s does that say?
Infinite amount of 9s.
infinite nines. If there are infinite nines, which again, explode, if there are infinite nines, it actually is 1. And that symbol is there are infinitely many nines. It is not less than 1. It is actually 1.
It's
So-
like kind of like taking thirds out of a 1, because it's all repeating 3s, but if you add all those together, it's only repeating 9. So like a third will never actually be a third unless it's to the infinity.
Mhm. I'll show you a little algebra really quick. If you've never seen this, you shouldn't be in calculus and nobody ever showed this to you. But I'll show you a little algebraic proof that this is actually 1. I'm going to set n equal to 0.999. I'm going to just throw a few 9s in here before I throw that symbol in, just so you can kind of get the idea that it goes forever. Now, by saying that's equal to some number, it now just became an equation, which means I can do equation stuff to it, right? Like for instance, if I decided to multiply both sides by 10, what happens to the other side?
Same thing.
It moves the decimal point 1 place over, does it not? Right? And so now I'm going to subtract these two. 10n minus n. I hope you're not still thinking the answer to that is 10. If you are, I'm worried about you for algebra. What's 10n minus n? What's 10 oranges minus 1 orange? It's 9 oranges, right? 10 oranges minus 1 orange is 10. It makes no sense whatsoever. You never would say that in the real world. 9n. But more interestingly, what happens on the other side? What's 9.9 repeating minus 0.9 repeating? Do you have less 9s here? Since the decimal point moved over 1, do you have 1 less 9 over there? The answer is no, if there are infinitely many of them. If there are infinitely many of them, you didn't lose any by taking 1 away, right? If I have infinite dollars and I take 1 away, I still have infinite dollars. So then when you subtract those two, you get 9. Now, of course, if you divide both sides by 9, I just proved that n is 1. That is not a trick. That isn't some nerd mathematician trick. But does it make sense that this is only true if there are actually infinitely many 9s? If there are less than infinitely many 9s, when you take 1 away, you have 1 less than you used to have. But if you have infinitely many, then you didn't lose any, and this is okay. So again, it's because infinity just is mind-boggling. That's the problem that you have here. So we're touching infinity. Okay, you're going to see some questions like this in your assignment, which are kind of dumb. But this is one of the things I'm going to show you because other math teachers that teach this would show this to you. And if you leave me before this term is over and go to somebody else, they're going to think you know this. But this is really contrived and it annoys me. So this is I want some question out of your book. 17. This is question 17 out of your book. So what we're looking at here is a really weird graph. Like we've been looking at real graphs like parabolas and stuff like that. But this is like some totally contrived, ridiculous graph. So let me give you a little bit of context. If you have a graph that looks like this, but there's actually like a little hole in it right here, that's kind of what we've been doing. Notice if you approach this point from this side, you land here. If you approach this from this side, you also land here. But what if your graph is broken and actually looks like this instead? Now, if you approach from the left, you land here. But if you approach from the right, you land somewhere else. This graph is broken. Mathematicians say that graph is not continuous. The reason I think this is kind of dumb is if you make up any ridiculous equation you want to, graphs are continuous. Like you have to work really hard at this to make a graph like this. But at least it teaches you something about theory. And so that's worth something. So we've been finding f of 3 and f of 2 and stuff like that. We've been finding it using an equation, but the question is, could you find it using a graph? In other words, let's look at question A up here. It says f of 1. Again, that's just code for x is 1. So you should say, well, this is easy. Duh. I'll go down here. Oh, I'm at x is 1. Notice you got lots of stuff to choose from. Well, where are you? If you're at x is 1, where are you? Like I'm going up there to find the graph, right? Where am I? I want you guys to weigh in on this. Notice there's a hole in the graph. Do you see that? The answer to this is not 2 because there's a hole in the graph. Where are you?
It's 3.
It's 3. Again, do you understand what I mean when I say this is really contrived? This is somebody just making a weird graph. Fine.
Yeah, like what data would this even represent?
None.
You know?
That's why I'm skipping most of chapter 2 because this is very contrived. Now, notice this second question B. Can you read calculus? What is that saying in English? If you show that to somebody in your family, they're going to think you're weird because it's like, what does that even say? But you should be able to put that in English and say, that's not really that complicated. What is that saying? It's like, what's the limit of f of x as x approaches 1? What's that little minus sign mean?
It means below 1. So
Below 1. So you're starting at 0.9 and then 0.999. And f of x is just y. In other words, they're just saying, what is y? It's the same question you just asked a minute ago. It's just saying, what is y if x is like 0.9 or 0.99 or 0.99? Well, isn't that the same exact spot we just were? Except they're saying you don't actually get to be at 1. You are here and then here and then here. You're getting really close to 1, but on the low side, right? Well, what do you see happening to y as you get closer and closer? What does it look like y is becoming? What's it look like y is going to be? It looks like it's going to be 2, doesn't it? Now, when you actually get there, it wasn't. But you see, the hole in the graph is the 0 over 0 that we just had a minute ago. It explodes. It doesn't work. And yet, when you got close, we still got an answer. So although you can't put 1 in directly because there's a hole in the graph, if you approach it from the low side, it appears that you're getting a y value of 2. It's on its way to 2. What does C say? C says the same thing, except for now you're approaching it from the other side, right? You're approaching from the high side of 1. And what does the graph say about that? Oh, I'm coming in from the high side of 1, so I'm coming in like this. Okay, what am I doing on the graph? Oh, that means I'm up here. Hey, I'm approaching 2 again. Isn't it on its way to 2?
I know this may sound like a really stupid question, but what if you were trying to figure out the function of y?
That's not a stupid
do-
question, and
doing it the other
that would be
way.
really hard because this is super contrived. Like you're going to have a hard time finding some equation that models this. Like you're not going to do it. And as a matter of fact, because there's a break in it, there's really like 3 equations there. You can't just make up one equation that does this. So again, this is sort of theoretical nonsense, but I at least want to show you something about limits instead of entirely skipping chapter 2. Now, this is really important. Notice from below, you thought it was 2. From above, you thought it was 2. Therefore, it's 2. Notice that just says what does y happen? What is y becoming as you get close to 1? Notice it doesn't say from which side. Just get close to 1. Well, from both sides, it's 2. Therefore, it's 2. Now, when you actually get there, is it 2? No, sorry, it's 3. The graph says it's 3. Let's look at the second place. You know, the other interesting place on the graph is right over here at 3, isn't it? Because there's another weird break in the graph over there. So let's go to that question. Let's look at G over here. What does y appear to be if x is on its way to 3, but it's coming from the high side of 3, 3.1, 3.01? What is the graph Where do you think you're landing if you're approaching X from the high side of 3? Oh, I'm up here, so I'm working my way. What is Y becoming?
1.
Becoming 1. Everybody agree with that? Again, chime in if you don't. Looks like Y is on its way to 1. Remember, this is the same thing we were just doing a second ago. It's just we were getting our answers. I'm going to change colors. Where's my... It's just that we were getting our answers from an equation. Does that make sense? We were just plugging numbers into an equation. And equations don't look like this. They don't have all these holes in them. So we just plugged it in and we saw it getting closer and closer to 10. It's the same exact thing. We're just taking it from a picture. Please don't make this hard. It's not. However, what happens if you approach this from the low side of 3?
It becomes 4.
Yeah, if you come at this from the low side of 3, basically it's like, oh, I'm on a totally different graph. I'm over here. Looks like I'm on my way, well, to 4, doesn't it? You see that?
This would be like trying to graph like data plot points from a survey, like, and trying to predict how people are gonna like answer questions.
Yeah, that's why this is kind of so contrived. The only thing I can come up with that's even close is kind of like if you go to the post office and you got a package and it's like, well, if you pay if it's 0 to 2 pounds, it costs $3. But if it's over 2 pounds, then it's $8. It's like you're in a totally different category. It's like, oh, you're on a whole new graph now. Or tax brackets. Like if you make less than 30,000, this is how your taxes work. But if you make over 30,000, oh, it's a totally different equation and you pay lots of money. I mean, it's not that this is totally unrealistic. It's just that this particular graph is contrived. Now what's the answer to this question? For some reason what's the answer to this question? What is Y as X gets close to 3?
Oh,
This
well,
is
the
not
graph
an
says
obvious.
2.
This is not an obvious answer at all.
It's 2, right?
Well, this answer is 2. For some reason my screen is sort of freaking out here, not letting me write. I don't think it likes writing on this picture very much. Maybe it's the color. Oh, my pen is dying. My pen needs charging. That's why it's behaving this way. That answer is 2. In other words, if I said X is 3, what is Y? Well, that point tells you where it is. But because on one side, you're thinking it's on its way to 1, and on the other side, you're thinking it's on its way to 4, the limit is actually doesn't exist. That wasn't very good. Again, these are kind of technicalities. In other words, what's it approaching? Well, from one side, it's approaching 1. The other side, it's approaching 4. So you can't say. Remember, in calculus, in a sense, we're never going to be able to do this. We're actually never going to be able to plug 3 in because that's going to make the slope 0 over 0. We're just going to have to get close to it. And this will never happen for us because we're looking at continuous curves. They're never going to have a big break in them like this. This is really just a theoretical concept. But this is a discontinuous graph. And so you'll notice in your assignment, this is why I'm telling you this, you'll notice in your assignments, they'll say, f of x is a continuous function. And you'll kind of read over like, why are you even telling me that? Well, this graph is not continuous. It's got a break in it. Continuous just means you can draw it without lifting your pencil. Because this graph has got a break in it, then we're approaching 1 from this side and we're approaching 4 from this side. So if you approach it from both sides, you don't get the same answer. So therefore, it isn't approaching the same thing. A second ago, we saw back here, did I even write this down? We saw this equation, when we got our answers by plugging them in, we saw it approaching 10 from both sides. And so we said, hey, look, it's 10, right? But what if it approached 10 from one side and 4 from the other side? Then what would you have said? You'd have said, well, I don't know what to answer now. Well, the only way that happens is if the graph has a break in it like this, which only happens when mathematicians are left alone to make up ridiculous questions, in my opinion. But you do have a couple of questions in your assignment like that. And I don't know. Maybe it's at least worth thinking about. I don't know. So tomorrow then, we're going to sort of spend all of our time with this algebra that we looked at today, like actually evaluating a limit without just kind of guessing at it. We're sort of done guessing. We're never going to guess again in this class after today.
Do we have class on Fridays?
No, I keep saying tomorrow, but I just mean next day. Sorry.
Okay, I just wanted to make sure because I have work in the morning.
No, I mean Monday. So you, between now and Sunday night at 11:59 and 59 seconds and 59 100ths, 59 60ths of a second. Now that you know calculus, you can really push it right to the edge in a way that you never could before. Between now and then, you need to be done with the MyOpenMath kind of practice that was in the introduction and in the algebra review, which you did a little bit of, and then 2.1 and 2.2. And then next week we'll start 2.3 and quickly get done with chapter 2, and we're going to start doing calculus. We're just playing around, getting our mind around the concept here. And incidentally, if you have time, look at the last section of chapter 2. Just do that in your book, and you'll thank me for what we're doing here. And it's actually not going to hurt you in calculus at all, but please take a look at it, because I just want you to understand people take this concept of a limit and just go to the end of the universe with it and kind of come up with every possible way to make this theoretically provable. And there's deltas and epsilons in there, and they talk about getting close to points, and delta is the distance you miss it in y, and epsilon is the distance you miss it in x. And most people utterly fail that section because it's so hard to grasp. And also the other reason I want you to look at it is just because it's like this stuff can be made to be really complicated when you write it down. Just like you know, in our language, if you try to explain what I showed you today to somebody that you know, and this is always true of math, that statement, what's the limit of f of x as x arrow 1 plus, like if you show that to any normal person, they're going to try to get away from you really fast. However, that's a really simple statement, isn't it? And I say that because you need to understand that all math is like that. If you read it in a book, if you go look at the last section of chapter 2, you're going to go, my God, this isn't even human. And yet it's a super simple concept. We aren't going to go over it because it's a waste of time, in my opinion. But that's true here too. And so you're not done with math until you agree that something is, oh, that's all that's saying. It's not that complicated. Calculus is not that complicated. But as I illustrated today, you're going to have to be able to, well, factor. Like you're going to have to know algebra. This wasn't that simple to get the answer 4/7, but you actually got to be able to factor. And I'm showing you the easiest equation that exists. We still have logarithm. We still have sine. We still have square root. We have a lot of ugly functions to kind of try to do the same thing to in calculus. And so the concept, I'm done actually teaching you the concept of calculus. There's nothing else to teach. You're done. But we got to go try this with other functions. Does that make sense? And that's where you'll get into the weeds. But it'll just be because of your algebra skills, not because of calculus. Right.
Mr. Gardner?
Yeah, call me Doug. Go ahead.
How soon do we need the textbooks by? Because South ordered them for me, and they did it kind of late.
You'll be okay. I'm not ever going to say, look at question 17 in your textbook, or, you know, I want you to do question 17 in your textbook. You need it just because you're going to need to refer to formulas, and, you know, I'm not going to cover everything that you need to know. And so you might find yourself looking in there and so forth. Any of the kind of take home problems that I give, I'm going to write them out anyway. And so, as I said, this class doesn't really get serious, in my opinion, until Tuesday, when we actually start talking about chapter 3, where we start trying to get these slopes a little, you know, then we're actually kind of doing calculus. So you're okay, actually, fortunately.
Thank you.
Yep. So stay after if you have questions to ask. Otherwise, boogie, and I'll see you Monday.
Hey Doug, just for fun, I was trying to prove the x minus 25 over square root of x minus 5. Do you mind if we just prove that real quick, just for fun?
Good question. Super good question. What did you try? In other words, you're trying to sort of show that it actually is 10 and not just wimp out like we were and just saying, well, it looks like it's on its way to 10. I guess I'll just quit.
Yeah, I didn't get very far. I just multiplied the top and the bottom by x squared to cancel the square root. So I got x squared parentheses like x minus 25 over 5x negative 5x squared plus x. I don't know if that's right or wrong.
Yeah, okay. I like what you're trying. So in order to, and again, what we're really wanting to do is just put in 25 for x, but we can't now. So you're saying, is there something I could do to that expression so that I could? And so, we can't factor it. So you said, oh, I don't like square roots. So what did you say you did? You multiplied top and bottom by what?
By x squared.
Squared. Now, if you don't screw that up, because I heard what you said, but I didn't write it down. But if you don't screw this up, that's distributive law. So if you do that, that'd be x cubed minus 25x. On the bottom, x squared times square root of x. There's a number of ways to write that, but I'll just wimp out for now and just write it as x squared square root of x minus 5x squared. I don't know if that's what you just said, but is that what you did?
I messed up on the numerator. I didn't do the x cubed.
Mm-hmm. So did you just leave you had x minus 25x squared?
I actually just didn't distribute it. I had x squared and then, yeah, x minus 25.
As I mentioned before, the algebra mistake that you will make will almost always be distributive law. So if you do it correctly, would you agree this is worse? Like you still can't put 25 into that. If you try it, you get 0 over 0. And it's even uglier than it was before. So two things. Number one, I compliment you for thinking, let's try to prove this. Number two, it's pretty hard to come up with like something that will help. So what you did actually didn't help, but that's the beauty of math right there. Like that's what makes it fun. If it was easy, it wouldn't be that fun and you wouldn't be proud when you got it right. So that's a good idea. Does anybody have another idea? Like what else might we try?
Wouldn't it be 25x squared on top?
Oh yeah, I got it wrong too. Thanks for bailing me out, Cody.
I have no idea. I have no idea how you'd make that easier.
It's pretty hard. If any of you knew, I'd be surprised. And I'll show you before we're done here. One thing you might think, because in a sense, this is what Connor was thinking, is like, that square root's bugging me. Can you square the top and the bottom of a fraction? Like if I can square it, isn't that how you usually get rid of square roots? So I could see somebody saying, I'm going to square the top and the bottom, and I could see somebody squaring the top and the bottom and getting this. That's not true algebraically. Do you know that? You can't square the individual parts. If you square x minus 25, squaring something means multiplying it by itself. And there's more to that. And again, what'd you do wrong? Distributive law. That's what you get wrong every single time. You just don't understand distributive law deeply enough. So the top is what I said, but it's also got a minus 50x up there. And on the bottom, it's the same thing. You've got, oops, that's not right. If you square the bottom, then you have to take square root of x minus 5 times the square root of x minus 5. That's what it means to square something. So that helped. So you get x squared minus 50x minus, I think that's 625. So you get square root of x times the square root of x. That actually helped. Yeah, right.
Plus 625, right?
Plus.
Negative 25 times.
Negative times negative. Thank you for rescuing me yet again. And then you get minus 5 square root of x minus another 5 square root of x, so minus 10 square root of x, and then minus 5 times minus 5 is plus 25. Now, is that helpful? The answer is yes, if you can put 25 in, but unfortunately, you still can't. If you put 25 into that, you still get 0 over 0. So you, again, made it worse. And that's only if you don't screw up your algebra. Or the second kind of mistake, dumb mistake, right? Which I've made two. You've already caught two dumb mistakes I made. One of them was, I guess I don't know that a negative times a negative is a positive. And I already forgot what the other one was, but there was another one.
The square.
Oh yeah, I left the square off. I left the square off the 25er. So My guess is you're out of ideas. Like, well, now what do I do? So here's the answer. And I wonder how long it took somebody to come up with this. Oh, actually, I'm sorry. I wasn't thinking. I think you actually might be able to put 25 into this. I'm not actually sure, but you can't square the top and the bottom of a fraction. I think I saw some of you saying, no, you couldn't do that. Let me give you an example. If I take the fraction 2/3 and I square both sides, or square the top, which is 4, and I square the bottom, which is 9, are those still equal?
Definitely not.
They're not. You can't do that to a fraction. The only thing you can do to a fraction is what you did up here, which is multiply the top and the bottom by the same thing. And the reason that's okay is because you're multiplying by 1. So you can't even do this. So, and we know the answer to this is about 10, right? So even if you could put 25 into that for x, which maybe you can now since you actually screwed it up, you won't get something close to 10. So it's like, that doesn't work. So here's what you can multiply by that I doubt you'd ever come up with, or, you know, like, where would you? The only reason I know the answer to this is somebody told me, you know what I'm saying? Like, at some point somebody taught me this, or I don't know if I would have ever thought of this on my own. Here's what you can multiply it by: the square root of x plus 5 and the square root of x plus 5. Mathematicians have come up with a name for that. It's called a conjugate. And the beauty of that is, watch what happens to this expression if you do this. So this is not simple. You still have to multiply everything times everything. So x times the square root of x is, well, I guess I'll just write it as x times the square root of x. And then x times 5. I'm going slow here to make sure I don't do something dumb this time. And then minus 25 square root of x. And then minus 25 times 5 is 125. But something really cool happens on the bottom. Which is this. You go x times the square root of x times the square root of x, which is x. And then you go square root of x times 5, which is the square root of x times 5, because there's no such thing as math with letters. And then you go minus 5 times the square root of x. And then minus 5 times positive 5, which is minus 25. Why is that really cool on the bottom?
It cancels out the 5 square root x.
Exactly. Now, you don't recognize this yet, but in the end, on the bottom, I have x minus 25. And what's cool about that is, what if I went back to the step before and I didn't multiply the top out? Isn't that what it looked like before I multiplied the top out? Why is that really cool?
Because it cancels out x minus 25.
Because those cancel out. And so this is now square root of x plus 5. And does it make sense? The prohibition against letting x be 25 is now gone.
Yeah, and then it adds up to 10.
It adds up to exactly 10. So notice how much worse that is. Like, you got to like know your stuff. You've probably seen conjugate someplace. You may have saw it with imaginary numbers. If you're taking like 4 plus 2i and you're dividing by 3 minus 4i, if you multiply the top and the bottom by 3 plus 4i, which is the conjugate of that statement down there, that's a way of dividing two imaginary numbers and getting an imaginary number. That's one place you might have seen it someplace. I guarantee you forgot that just because it's so non-applicable. It probably went away, but this little trick of a conjugate comes up now and again. But you got to see this as just like any other thing in life. It's like woodworking. You know, I'm putting the trim on my house, and it's like, oh, the sheetrock is sticking out too far. And you know, and some person who's really good at it says, oh, look at this cool trick I learned is how to fix that. Like, doesn't that happen everywhere in life? So it's like, this is just the math version of that. It's just one of those tricks. You don't need it very often, but when you do, it's really cool. I could have given you like 3 hours on that and you never would have come up with that crazy idea, right?
Well, if I was just, I started kind of getting it once you like ran me through a bunch of stuff that didn't work, but I don't think I ever would have came to it on my own.
Yeah. Well, and again, I'm your teacher, but I wouldn't either. Like, I'm not that guy. I'm not super creative. And although I really do like math, I would rather ride my mountain bike. As soon as I'm out of class, I'm probably going to ride my mountain bike. I'm not going to sit there, you know, close all the drapes and theorize about the beauty of math, even though I think it's beautiful. I'm just, there is Netflix. Like, I think if I did live back like Archimedes, and I don't have mountain bikes, I don't have kayaks, and I don't have a car, I can't drive anywhere, I probably would really get into this. But I doubt in our world there's too much of this stuff that gets invented anymore, because there's just funner things to do. I mean, they're dumber in one sense. It's like, oh, watch Netflix, but
That's a way to think. I didn't think about it like that, but you're correct. Thanks for walking me through that, Doug. I'll see you Monday.
Nice question. Good job. Anybody else?
Only thing I would have to add to that whole thing is that sheetrockers will always make your life miserable.
So true. So true.
Like, I don't know how many times I've seen electricians just beat a hole through a wall because the sheetrock guys covers up the box.
Yeah.
Like, now you can go back and fix that.
What have you done?
Level 5 finish.
What do you do? Why do you know about that, Andrew?
Just like I've worked in a lot of jobs.
Okay. Yeah.
So it's just like something I've seen happen before. Like, I worked for my dad's company when I was in high school in summertime, and we did a lot of stuff. Like, we did a lot of bathroom remodels and stuff, and we'd be going behind contractors that screwed it up. And so, like, we'd have to go back and fix everything and be like, where's the outlet box for this GFCI we have to install? Oh, it's behind the sheetrock. That's cool.
Yeah. The funny thing is, the electricians show up and they don't know their plug's covered up, because they wired this like 2 months ago, and they've wired 50 houses since then. So they come back and hook everything up, and there's like a whole set of circuits that's dead because that one box, their wires aren't wired together, and they have to kind of find it in the house. It's not even in the bathroom, because there's one in the bathroom. It's just somewhere in the house, and then they find the little bulge in the wall that's sticking out a half inch, and it's like
yeah. Sheetrock guys are.
I worked on a 9-month project as a sheetrock guy, and we were building a retirement home, double layer 5/8. We covered up, I don't know, probably 6 of their boxes. They got really pissed. The day